Okay, in this video we're going to take a look at section 2.5, which covers some different applications from physics, and it talks about work basically. So before we can get into any examples, I'm just going to take the beginning of this video to review some concepts from work. And I realize for some of you it may be review, for others of you may have never seen this before. So hopefully it is something you've seen before. The first thing is that when you're talking about work, we always think of work as force times distance. And so typically you will see a formula written like this: W equals F times D. And of course, W is work, F is force, D is distance. And so that kind of brings up the next thing. Well, since work involves force, we need to review what force is, and we really need to kind of look at that from both the English system and the metric system, because they are just a little bit different in the way we work with them. So the first thing, let's look at the metric system. In the metric system, we typically write it for our applications, we're going to be writing force as being equal to mass times gravitational acceleration. We're only going to be dealing with forces due to gravity. And so when we think about that, we need to talk about sometimes in some of our applications we're going to be looking at, we need to calculate mass, the mass of water. So let's write up here. If we're talking about the mass of water, then we will be finding the mass by using density. So we will take density, that's rho, times V, which is volume. So we'll kind of write that on the side here. Let's say density times volume. Typically, units there would be something like maybe, so since we're in the metric system, it would be kilograms per cubic meter times cubic meters, which of course then the cubic meters would cancel and we'd be left with kilograms, which is our units of mass. So that's one thing we needed to review there, for if we're dealing with the mass of water. And then the other thing we need to review is what actually G is. So G, if you will, is what we call gravitational acceleration. This is the acceleration due to gravity. And that's a different value depending on if we're in the metric or the English system. So in the metric system, we're going to use G to be 9.8 meters per second squared. All right, so that's for the metric. If you are dealing with the English system, then G is going to be 32 feet per second squared. Okay, now let's go ahead and talk about force for the English system, also sometimes called the British system. So for the English system, always think about force as being some sort of weight. And a lot of times the formula that is used to find force in the metric system is taking density times the volume. Density times volume. Okay, so let's jump in a little bit more and talk a little bit more about the units. So in the British system, the force unit, remember force is a weight, and so the one they use there is pounds, and abbreviated LBS, whereas in the international system, the units for force is a Newton. So in Newton, symbolized by N, is what you get when you take a kilogram times a meter per second squared. And that follows with our formula M times G. Kilograms is the units for mass, M, and then meters per second squared, we already talked about, is the units for gravitational acceleration. And again, this is called a Newton. Then we talk about distance units. So in the English or British system, the English system as well. In the English system, the distance unit is feet, whereas in the metric system, the unit is meters. We abbreviate this as FT, abbreviate this as M. And so our work unit, again, work equals force times distance. In this case, we have pounds times feet, or we write that as a foot-pound. These are foot-pounds. And then in the metric system, again, we take force times distance, so that's newtons times meters, or Newton meters, which are joules. These are joules. And a joule is equal to a Newton meters. Okay, so hopefully that was a review for you, but if not, these are all things you need to become familiar with. Now that formula, work equals force times distance, that's what we use if the force is constant. Everything's simple if the force is constant, but sometimes we have a variable force, a non-constant force, and that's where the calculus comes in. So what we then think about is we have to think about the dW as being the infinitesimal amount of work that's done by that variable force. And we have this definition that says that work is equal to the integral from A to B of the force function dx. Let's jump into some examples to see how this works. Examples 1 and 2 are two simpler ones, and then we'll do example 3, which is a little bit more complicated. Example 1 says how much work is done when a 500-pound iron beam is hoisted 30 feet in the air. Notice the first thing we probably want to talk about is what system are we in, and since it says pounds, so we are going to be in the English system. And remember, again, work equals force times distance. And so in this case is our weight. Remember, for the metric system, for the English system, our force is in pounds. So this is 500 pounds times the distance, and it says hoisted 30 feet in the air. This is not a variable force. It is a fixed weight, a fixed force. So 500 fixed pounds, not changing, times 30 feet gives us an answer of what? Well, you did that calculation, but that's 15,000 foot-pounds. Okay, so that's a basic physics application, no calculus needed there. Let's take a look at example 2. And notice again here, it says there's a little note to watch out for units. Right? Get in the habit of writing your units down. You lose points on the test if you don't keep track of the units. Example 2 says, how much work is done by a weightlifter in raising a 60 kilogram barbell from the floor to a height of 2 meters? Okay, so notice now we're looking at kilograms, we're looking at meters. This is going to be the metric system, just recognizing the units. And so again, work equals force times distance, but remember for the metric system, force is equal to mass times the acceleration due to gravity. So look at our mass. It says there's a mass right here of 60 kilogram for the barbell. So we have 60 kilograms times the acceleration due to gravity, which if we look back on the previous page, we said that in the metric system, gravitational acceleration was 9.8 meters per second squared. So we can go ahead and calculate that. Multiply that quantity out. 60 times 9.8 is going to be 588 newtons. Which then allows us to find the work, because again, work is force times distance. And we now know the force is 588 newtons. We want to raise it to a height of 2 meters. So multiply that by 2 meters. 2 times 588 is 1,176 joules, which is, remember, joules are what we get when we multiply newtons times meters. All right, again, the force is constant because we have a weight of 60 kilograms. So now we're going to get into one where we need to use some calculus. This next example is a little bit more complicated. So if we look at example 3, it says a uniform steel chain 100 feet long and weighing 1,500 pounds hangs vertically from a pulley system at the top of a building. Find the work required to pull it to the top. So if you want to kind of think about it, there's your building over here that has a pulley system attached to it. This is our building. And we have a chain that's hanging off of this pulley that's 100 feet long. And we want to think about, so if you break up this chain into a bunch of little infinitesimally small pieces, if we took a piece of the chain down here, that infinitesimal small piece of the chain has to move a farther distance than, say, if we took a piece of chain here. That one would only have to move about that distance. And so this is where the calculus comes in. Each part of this chain has to move a different distance, meaning there's more weight involved for each chain, right? Each part. Because once you, maybe another way to think about it is once you pull some of this chain up, there's less weight that's hanging, and so there's less work required. So I'm going to let me erase what I just drew here, and this is the way we kind of think about a problem like this. We take, let's say, okay, let's draw out a little segment of this chain right there, and let's call this the width of this chain. Let's call it, that little segment, let's call it delta x. And let's think of this as like our x-axis. And for a lot of these problems, it's easier to think of the part that you're pulling to as your zero. So remember, we have 100 feet of chain. So if we make right at the pulley to be 0 feet, then that means down here at the bottom of the chain, this is going to be at 100 feet. Now I know that's opposite from what we're used to seeing. We're used to seeing, you know, instead of going 0 to 100 is going down. We usually see that going up, but we can set up our axis however we want. It doesn't really matter. And so this piece of the chain, this little piece of the chain has to move a distance of y, or x, excuse me, has to move a distance of x, and it's going to be different for each little piece of the chain. So let's say for this little piece of the chain, let's say the distance it moves is not x, but xi. And what system are we in? Are we in the metric system or the English system? So if you read through the problem again, because it's feet and pounds, what system is that? That is the English system. So let's real quick go back to the first page and review English system. Remember, for our English system, well, work is still force times distance, but then we need to think about the weight of the chain for the force. So if I come back here, we know that the chain weighs 1,500 pounds total, but we're talking about just a small little piece of the chain. So in order to do that, we need to first find the unit weight of the chain. The unit weight of the chain. And to find a unit weight, you just take the total pounds divided by the length. So we know this chain weighs 1,500 pounds, and it is 100 feet long, which means the unit rate is 15 pounds per foot. It means that for every foot of this chain, the weight of that foot of chain is 15 pounds. So how much then is the weight of this infinitesimally small piece of the chain? How much is that right here? How much does that weigh? Well, if it weighs 15 pounds per foot, you just take that weight per foot and multiply it by the thickness of the chain. How many feet long is that infinitesimally small piece of chain? So let's say, what is the weight of the infinitesimal small piece of chain? And if we can find that, that's going to give us the force for that weight. So again, we take the unit weight, we take the 15 pounds per foot, and we multiply that by the length of that infinitesimally small piece of chain, which in this case is just going to be delta x feet. And of course the units cancel, so this is equal to, right, which units cancel? The feet cancel, so feet cancel. So we get 15 times delta x pounds. So if that's the force, then what is the work that's needed to lift that piece of chain? What is the work to lift the infinitesimally small piece of chain? Well, work equals force times distance, right? So work equals force times distance. And remember, going back to our picture here, this delta x, this small piece of chain, is going to move a distance of xi. We already said that, we already know what the force is. The force is 15 times delta x. 15 times delta x, that's the force, times xi. And that allows us then to find our work, because we can now use the integral. The work is going to be the integral, and this is an integral with respect to x. The distance that, for x, that we're moving here, well, if we're at the little small piece of chain that's at the very top here, it's not moving any distance. And then down at the bottom here, it's moving a distance of 100 feet up. That little piece of chain down at the bottom would be moving up 100 feet. So this is going to be, x is going to range between 0 and 100. Just taking this expression and moving it into here, we have 15, and we have x, and then the delta x is going to be our dx. And then we just integrate that. Take the antiderivative, we get 15 over 2 times x squared, going from 0 to 100, which is going to give us 75,000 foot-pounds. So that's the work to lift up the chain. Now, let's now add something to this problem. Let's say that at the end of this chain, so down here at the bottom, attached to the bottom is a big steel beam. It weighs 500 pounds. It says find the work required to pull the chain and the beam to the top. Well, the beam is a fixed problem. There's no calculus required. The work needed for the beam is just going to be simple force times distance. It has a force of 500 pounds, or a weight of 500 pounds, times the distance. That if that beam is at the bottom, the distance it moves up is 100 feet. Times 100 feet is 50,000 foot-pounds. And so then the total work is just the work of the two pieces we just found. It's the work of the beam plus the work of the chain, or needed to move the chain. And so that is 50,000 foot-pounds plus 75,000 foot-pounds is 125,000 foot-pounds. And that's the answer to example 3. And that's going to do it for this video. We are going to have a couple more videos for this section. So I will see you in the next video. Thank you.